Lab 2 Motion of a Falling Object. The purpose of this lab was to observe and analyze the motion of a falling object that was dropped from rest through tracker and compare its motion to that of a computational model. Its motion when tracked was accelerated first when it dropped, but then reached its terminal velocity due to the effect of a net force, which contributed both of a drag force and weight force. The terminal velocity is the point at which the object no longer accelerates, because the air resistance, or drag force in this case, pushing up against the object becomes equal in magnitude of the weight force of the object. This does also explain how the object is not free-falling, because a free-falling object would only have the force of gravity acting upon it, never reaching terminal velocity. The drag force is the force that is exerted on a solid object that moves through a fluid medium. In this case, the medium would be air. The drag force always increases as the speed increases, and when it eventually reaches the magnitude of the weight force, the object reaches terminal velocity. This will later be observed when comparing the computational and observed models. The motion of an object can also be explained by Newton's second law of motion, which follows this equation, that the final velocity is equal to that of the initial velocity plus the net force acting on the object divided by its mass multiplied by the change in time. Since there is a net force in this lab contributed by the drag and weight forces acting on the object, there will be acceleration, at least at the start of the object's motion, as we will later see. Here, I am dropping a paper cube at a height of around 5 feet 2 inches. However, I started tracking my data once the object had already left my hand, so there would not be any discrepancy in the motion data. However, I later found that I could have still started tracking the data from the initial point of release without having any discrepancies. Nonetheless, the resultant information here still describes the motion of the object and the effect of drag and gravity effectively. Based on the observations from tracker, a computational model was prepared. The initial conditions of the mass, velocity, and position were changed. The delta t was kept really small to increase the accuracy of the predictions. Here, the final time was matched to that of the observed final time. Then Newton's second law was incorporated into calculating the final velocity and final position of the object. This time, a gravity variable was also included to describe the object's motion. J hat represents the vector form used to calculate the net force along with the object's mass and weight force. In a comparison graph between the model's prediction and observed motion of the object, it is noticeable that the model overpredicts the motion of the object by quite a bit. This is due to the fact that only the weight force was accounted for in the code in VIDLE. The drag force should also be used. As we explained, the drag force is the force that is exerted on a solid object that moves in a fluid medium. The solid object is my paper cube, and the medium is the air. In the code, the drag coefficient B was also modified until the final position predicted by the model was similar to that of the final position of the object when dropped. B was later used in the calculation of the drag force, Fd, with the equation negative B times the object's respective velocity at that time. This was then added to the weight force to obtain Fnet, or net force. Finally, in a comparison between the model with drag and the observed model, the curve seems to match almost exactly. Here we can see the object accelerates in the beginning with the curve in the line. However, it later seems to reach a constant velocity and produce a straight line, indicating the terminal velocity. In conclusion, the net force does not equal 0 in this lab due to the effect of the drag force and weight force. However, the object does reach constant velocity when the drag force equals the weight force, which produces a net force of 0 later on in the motion of the object. What does it mean? Which models predict the terminal velocity? Well, the second model, with the inclusion of the drag force, predicts the terminal velocity due which describes the opposing force of air resistance to the force of gravity. When the two equal each other, the net force will equal zero, and the velocity of the object will become constant. In this case, the terminal velocity seems to be around negative 2.5 meters per second. What if? Would the terminal velocity, in the case where an object was thrown rather than dropped from rest, would be the same or different? Terminal velocity depends on the mass of the object, the density of the medium it's traveling through, and its surface area, none of which change when the object is thrown versus dropped. Therefore, the terminal velocity would be the same even if the object were thrown. However, since it is thrown downwards instead of dropped from rest, it would probably the acceleration of the object would, instead of speeding up to a terminal velocity, it would slow down to its terminal velocity because the drag force would initially be higher than the force of gravity. In this velocity versus time graph of an object thrown downwards, the velocity seems to decelerate as the object moves downwards and reaches a flattish line indicating terminal velocity.